get us busy. Thank you very much. I think, Bill, that we can start because
yes,
we are
fine.
already. Yeah, okay, thanks. So thank you very much for joining us today, and I apologize for the little delay. As I said, we had some technical issues that we hope they can be solved, because one of our speakers today, the speakers from China, she's having some issues to connect and to share her screen, but we hope this will be solved in the next minutes and we can have her presentation. So welcome all. I'm very happy to see you again. This is already the fourth edition of our series of East-West workshops. So good morning, good afternoon, and good evening, depending on where you are in the world. Many of you already know me. I'm Juan Manuel Cano Sanchez from the University of Science and Technology, Beijing. I am an associate professor at the Institute for Cultural Heritage and the History of Science and Technology. And I do also belong to the Association for Industrial Archaeology. I'm the young members board of the Association for Industrial Archaeology. As you know, this series of workshops are organized together by the Institute for Cultural Heritage and the History of Science and Technology and the Association for Industrial Archaeology, together with the Young Members Board. So the main aim of this series of workshops is to exchange ideas from people, colleagues and friends from the East, the West and beyond about industrial archaeology, or about the archaeology of the industrial past. But as you know, we take this with plenty of flexibility. We are very flexible with the chronological borders of this industrial past, and we are also very flexible with the disciplinary boundaries of the different disciplines interested in the industrial past, because that flexibility, that diversity has always been a characteristic of industrial archaeology. So today's meeting is going to be focused on the archaeology of technology. That is, we are going to come back to that initial technocentric approach as defined by Dr. Mike Neville, that characterized industrial archaeology in the West for the first decades, and it is still, I would say, characterizing industrial archaeology in the East, at least in countries like China. So we are going to revisit, we are going to rediscuss this interest in technology with new geographies. And when I say new geographies, I mean that this time we are even going to leave planet Earth. So we will also have a look at the technologies for space exploration. New chronologies too, with hopefully Feng Shujin will be able to share her presentation, and we will see how the history of technology, or how industrial archaeology can be a little bit longer from a chronological perspective. And also, we are not going to be only discussing about the history of technology from the point of view of archaeological or historical explanation, but also from the point of view of the technical conservation and the technical restoration of its material remains, mostly machinery and pieces of engineering. So I don't want to take any more time from the speakers, but do let me please share a pair of practical advices to keep the workshop as smooth as possible. We are going to have 3 presentations of 30 minutes each. And during this presentation, please keep your microphones and cameras off so we can focus on the presentations. At the end of the workshop, in the last half an hour or so, we will have plenty of time. So in that moment, everybody is very welcome to use her microphones and cams to exchange ideas, make questions, and discuss. In the meantime, please feel free to use the chat facility here in Zoom to share your ideas, questions, or any opinion that you want to share. And also, I know that for many of the attendees here today, and that is also my case, English is not the first language. So if you have any difficulties listening to the presentations, there are captions available. So you can click on the CC button on the bottom of your screen and you can read what we are talking about. So that is all I wanted to say. So thank you very much again for joining us. Thank you very much, Bill, for taking care of the technical side. And let's move to the first presentation that I do believe that everybody is very much looking forward to, at least I am. So first presentation is going to be Beyond the Rocket, the archaeological study of space technology, and it's going to be delivered by Associate Professor Alice Gorman from Flinders University in Australia, who is better known perhaps on the internet as Dr. Space Young. So she has a very wide expertise on Australian indigenous archaeology and heritage, but she's not here today to talk about it. And I will say that internationally, she is better known for her contribution to the field, to the very new field of space age archaeology, or the archaeology of space exploration, to the point that her work in this field has even been acknowledged by giving her name to an asteroid 551014 Gorman. That, well, for me, that is something very impressive. I don't know how many of you have your name given to an asteroid, but probably only Alice Gorman here. Also, she's very well known because of this book that I totally recommend you to read. I just finished it yesterday, and I must say that, well, there is plenty of knowledge you can learn from this book, not only about space age archaeology, but about space exploration in general. But even more, it is a book that I really enjoy reading. It is like very good, high quality literature. So you can learn many things and at the same time enjoy while you are doing so. And lastly, I would like to mention that last year, Alice Gorman, together with Justin Walsh, they co-directed an archaeological survey in the International Space Station that so far it has been the first archaeological fieldwork that has ever taken place outside planet Earth. I think that all of this is very impressive. All of us are very much looking forward to knowing more about this. So please, Alice, the floor is yours.
Oh, thank you, Juan, for that very lovely introduction. And I am indeed going to touch on some of the things that you mentioned. First of all, can everyone see the screen, my screen?
Yes, we can.
I apologize for the quality of my voice, which is suffering a little from a bronchial infection. But I'm very pleased to be here. And I would like to start with an Australian tradition, acknowledgement of country. So I would like to acknowledge that I'm joining you today from the traditional lands of the Kaurna people of the Adelaide Plains. I acknowledge their deep and ongoing cultural connections to their lands, waters, and perhaps most relevantly for tonight, their sky country. I pay my respects to their elders past and present, and extend that respect to the traditional owners of all the nations who are joining us today in the audience. So I'm going to talk about some aspects of how we study the technology of space exploration. So just to introduce this, what are these places and where are they? So we have a broad range of kinds of site, which range from the ground segments on the surface of Earth. These are places where rockets are launched. I'm not going to dwell too much on rockets because I'm going beyond the rocket today, but rocket launch sites are obviously a very important part of the technology, heritage and history of space exploration. There are also around the globe tracking stations which monitor their movements, collect data, send commands, and all kinds of research and development and testing facilities. So this is the kind of space archaeology you can do on the surface of Earth. There's plenty of it. In the space segment, we have a huge amount of material currently orbiting Earth. We have numerous spacecraft orbiting other planets, including the Moon, Venus, Mercury, Mars, a few in the outer to middle solar system, and of course, planetary landing sites as well, spread from here to the moons of Saturn, places where human spacecraft have touched down on another celestial body. And finally, deep space is considered basically to be around about where Mars is, but in deep space, we have a number of interplanetary probes, of which the most famous are possibly the Voyager 1 and 2 spacecraft, which are currently outside the solar system. So this is the range of stuff, the archaeological material that we can study as industry and as technology. I would like to focus particularly tonight on the stuff that is outside Earth. So this is all of those things in different orbits and throughout the solar system. There are a few interesting characteristics of this material culture. First of all, we could characterize it as a machine landscape. It's a cultural landscape of sort, a combination between the activities of humans and the natural space environment. But it's a machine one. Apart from the International Space Station with a tiny number of people on it, and sometimes on Tiangong as well, a small number of people. Basically, everything we have put into space is abiotic or robotic. We make machines capable of withstanding the incredibly harsh conditions of outer space, and we make them to operate without human intervention, unless it's remotely from Earth. So this is a landscape of robots. This is a population, effectively, of robots. It's not like us. It's not how we live. It's also an environment which encompasses a number of different types of gravity. So if you take the average spacecraft, it will be launched from the surface of Earth in one Earth gravity. It will experience acceleration and deceleration, but will often end up in orbit where it is in what we call microgravity. Effectively, it's in free fall. So these objects, unlike human bodies, which pretty much stay at the same gravity all the time, have to move between different extremes of increased gravity and the effect of no gravity, and move from environments which include the moisture and living ecologies of Earth into outer space where they're subject to extreme temperature differences and intense radiation. So for this stuff that's outside the Earth, we don't have the luxury, as it now seems to a space archaeologist, to actually physically go there and study it. This means we have to develop some new methods to study the material culture of outer space. And these include adapting those that we do already use on Earth, things like remote sensing from Earth or space-based instruments, and developing creative ways of image analysis, since one thing we do have no shortage of from some of these missions is imagery. So, of this stuff, there are a whole range of different kinds of research questions that we can ask. Some of the most interesting and maybe obvious to me include looking at how space installations and spacecraft change over time in response to how we understand the space environment, what we learn about what it's like outside Earth, and how we adapt our materials and technology to survive that situation. But it's not pure technology, as everybody in this room knows. Change in space technology and the kinds of things we do is also very responsive to political and social factors. And a big part of this is what we call space power, defined here as the total strength of a nation's capabilities to conduct and influence if things from space to perceive its objectives. So space isn't all about science and exploration. It is a highly political activity, and much of it is motivated by the relationship of different nations to space power. Other questions I think are critical are looking at how technologies developed on Earth change as we send them into space. So what is different between Earth and space? The nature of that variation, how it changes over time, and how we are now evolving distinct cultures and material cultures that belong to space, that are no longer of this Earth, if you like. Additional factors are looking at engineering traditions, often called engineering heritage, and to see how they are distinct to different nations, cultures, organizations, all of that kind of thing. And a question which is of interest to both space industry and to archaeologists is taphonomy, how things decay. This has practical applications for space industry, of course. So with these research questions in mind, I'm going to use 4 examples to briefly pick up on some aspects of this. I'm going to have a look at amateur spacecraft in Earth orbit, the International Space Station, which, as Juan mentioned, is a project I'm currently working on, aspects of how humans use material culture to engage with the moon. And finally, I'm going to use an example of indigenous space technology. Now, I hope I'm going all right for time, and Juan, I will rely on you to give me messages if I'm getting close. But let's start with amateur spacecraft. This picture shows you a whole range of amateur spacecraft currently orbiting Earth, most of which are classed as space junk. And these are very different to the national corporate space agency scientific spacecraft that we see. So in terms of their context, their situation, many of these are part of a large population of stuff orbiting Earth, which we call space junk. And this is a simulation. It represents approximately 35,000 objects ranging from fragments 10 centimeters in size to whole spacecraft the size of 2 double-decker buses. And below that size, there are millions and millions of tiny, tiny fragments of junk. So most non-operational spacecraft are classed as junk. And among those pieces of junk is one of my favorite all-time spacecraft. This is the amateur satellite Australis Oscar 5, which was launched in 1970 and is still in Earth orbit. It's part of a long tradition of amateur satellites. In fact, it is the 5th in the series launched by the US organization AMSAT. And even though it was built on a very low budget, they were a group of students from Melbourne University who had no money, no resources to speak of. It was also a hugely successful satellite. And among its innovations were being the first remote-controlled amateur satellite, getting some very successful scientific data, and creatively using existing technology. The antennas that you see on the spacecraft are actually retractable steel measuring tapes of exactly the kind that archaeologists like to use when we're excavating. So they're very useful to make into antennas that can be released once the object is in orbit. So this represents a whole tradition of space technology done on a shoestring budget that is very different to the spacecraft that are vaunted for their historical achievements and incorporated into stories of national prestige and national achievement. So I think this makes this and its amateur cousins in orbit at the moment make a very interesting counter-narrative to what we think of as space technology. Now moving on to the International Space Station. And this is where Justin Walsh from Chapman University and I recently conducted the first archaeological fieldwork outside the Earth. And this was called SQUARE, the Sampling Quadrangle Assemblages Research Experiment. We had to make a fancy acronym because that's what you do in space. And we had to have a fancy mission patch because that's what you do in space as well. So this is our wonderful mission patch. The idea behind this fieldwork was basically to set up 6 1 by 1 meter squares that we would sample using photographs over a period of 2 months to watch how objects moved in and out of them. And we successfully completed this fieldwork. Obviously, it was done by the crew. We weren't able to go there, but we had all of the data gathered last year, and we're now moving into the analysis phase, I guess. So this is one of our squares. It's in the Node 1 galley area, which is where people take their meals. And while we haven't fully analysed the data here yet, there's a couple of interesting things to notice. One is the presence of Velcro patches, which are quite filthy, which indicates one of 2 things: that they've been there for a long time, and that's quite possible, or that they're in high rotation use, even though most of them are empty at this point in time. So Velcro, it turns out, a very simple material used all the time on Earth, has a big function to play in microgravity space habitats. And it's part of a suite of technologies that we're calling gravity surrogates. These are things that stand in for gravity. So on the International Space Station and other space stations where effectively in free fall, gravity can be replicated in little patches which are spread throughout the station's interior. They might be Velcro. They might be Ziploc bags, which are exactly the same that you might have in your own kitchen or office or garage on Earth. And you can see plenty in this picture here. There's barely a photograph of the interior of the International Space Station, which doesn't have Velcro or snap cloth bags. And there's a whole array of hooks and straps and bungee cords and meshes that are used to fix things in place, to make a little tiny piece of gravity at that one location. So we have a really interesting correlate of these tiny bits of inconsequential material that actually structure behavior in a microgravity environment. And this is one of the things that our research is planning to elucidate further when we get into the analysis. So let's move on to the moon. And here I want to look at another piece of quite simple technology. So this picture here shows you Harrison Schmitt, the geologist who was on the Apollo 17 mission, the last one to the moon in 1972. And you will notice that he is covered head to toe in dark lunar dust. So we have 6 missions that landed on the surface of the moon, and you can see all 6 of them here compared, imaged by the Lunar Reconnaissance Orbiter, mostly discernible by the shadows that the hardware cast on the tracks. And we can see from Apollo 1, each successive mission, stayed for longer on the surface. With Apollo 15, they added increased weight. They added the lunar surface rovers, which further extended their geographical range. So we have a process where you start from this one little exploratory venture through to more sophisticated and mature missions, which kind of know what they're doing. So across these 6 missions in just 6 years, we have a process of adapting to a very distinct planetary environment. But something these astronauts found, there we go. It was not unexpected that lunar dust would be problematic, but when they actually got to the surface, it was discovered to be a major hindrance to almost everything that people wanted to do. So much so that by the second last mission, Apollo 16, the commander, John Young, said dust is the #1 concern in returning to the moon, and that remains true today. On the cusp of new missions to the lunar surface, the dust problem is still a major one. So while it was anticipated, the Apollo astronauts left with equipment to try and get rid of the extremely fine and abrasive lunar dust. they didn't entirely solve the problem. So the spacecraft left with vacuums, and you can see a picture of one of these little vacuums here, and various kinds of brushes and cloths so they could get rid of this abrasive sticky dust, which is in fact a health hazard to breathe, before they took back off for Earth. And each mission tried new things and had different successes and failures. So on the Apollo 16 mission, the little vacuum cleaner, which had been continuously improved since Apollo 11, actually ceased working because it got clogged up with dust. On Apollo 14, they developed some better covers for the fan filters in the cabin that were able to filter out the dust so they didn't return home with a cabin full of this quite nasty stuff. So we had an iterative process where each mission learned from the previous one until they got things more or less okay. And these are lessons that will be incorporated into the forthcoming lunar missions as well. So this was an interesting feedback between practical knowledge of how lunar dust behaves and the technologies available to try and manage it. And I find this quite fascinating personally. Now to finish, and I hope my time is still going all right, I do actually want to incorporate an aspect of Indigenous technology into this story. And just to warn anyone in the audience, there is going to be some images of deceased people coming up in this slide. The picture I'm showing you here is a boomerang that was taken to the International Space Station in the screen there by astronaut Shannon Walker in 2021, made by Ghana man Jack Buckskin from Adelaide, where I live. So this is going to be a little sideways trip into a deeper form of science and technology. So when European geologists started exploring, if you will, areas of Central Australia, they were very interested in finding strewn fields of tektites or australites. These were glassy, dense nodules of melted material formed when meteorites hit the surface of the Earth or exploded in the air, which had incredibly aerodynamic shapes. And in fact, in the early days of their study, it was unclear where they came from. One of the theories was that they in fact fell from the moon because the shapes of these little things indicated falling at speed while in a molten state. So as you can see in this picture here. Now, the traditional owners of the areas where you find tektites also had this theory. They posited that these had fallen from the sky, quite likely the moon. What's interesting about this is that this indicates a quite sophisticated theory of gravity. Now, it turns out that they don't come from the moon, although this was widely thought for a long time. But their aerodynamic shapes remain intriguing, and I think are a window into Aboriginal ways of understanding the natural world. So let's extend that theory of gravity to the work of the great Ngarrindjeri scientist David Unipen, who was born in 1888 in the Rakan mission in South Australia. So the device known as the boomerang had been used by Aboriginal people, obviously for many, many thousands of years, but Unipen was interested in its aerodynamics, and he was interested in it from a physical and mathematical point of view. And he did a great deal of research on how boomerangs actually worked. As a result of this research, actually, I won't tell you, it's a spoiler, I won't tell you that. Anyway, let's just take it. He did a huge amount of research, and he was a superb mathematician as well. Boomerangs, as it turned out, have flicked in and out of a number of space situations. So they've been taken to the International Space Station a number of times. Here we see a picture of an experiment proposed by Malaysian and Indonesian high school students in 2014. An astronaut, Narishi Kanai, flew these little boomerangs. You can watch the video if you like, to see how they behaved in microgravity. So there's a lot of interest around this simple and yet incredibly sophisticated technology. So more recently, we've actually seen an extraordinary aerodynamic feat, which was the flying of a helicopter on Mars, little Ingenuity. Now, this brings me back to David Unipen. So in 1914, which is 22 years before the first helicopter was invented, based on his study of boomerang aerodynamics, David Unipen postulated that using these principles, as he says here, an aeroplane can be manufactured that will rise straight into the air from the ground by application of the boomerang principle. So this Ngarrindjeri scientist basically invented the helicopter, which has now ended up on the surface of another planet. And this great scientist is honoured in Australia by his picture on the $50 note, which you can see here. So this is taking a little sidetrack beyond the rocket to look at how we might tell different stories about space technology by taking different perspectives. And this, I think, brings me to the end. And my conclusions to this story, I guess, are a few. So I find these small objects in many ways far more fascinating than the fancy technologies of rockets and antennas and space station modules and lunar landing vehicles. Looking at how a bunch of students might put together their own satellite, looking at how objects like Ziploc bags and bits of Velcro might be used in space, how we would manage dust, and the very ancient technology of the boomerang, how it could be used in space, I think gives us a different perspective that isn't just about the big spacefaring nations and the fancy technologies like rockets. But I guess all of these, excuse me for a second. All of these objects and stories, in a way, are about a similar thing. They're about what is different between space and Earth. What stays the same? What do we have to change? And there are two aspects to that. One is the materials themselves. So the external materials of a satellite have to be a bit different than a metal thing on Earth because of the conditions that they're subject to in the space environment. But other things are identical. Those Ziploc bags and bits of Velcro are exactly the same, chemically and structurally, as the ones that we use on Earth. The second thing that's different is behaviors. So the behavior that is generated by or controlled by the use of Ziploc bags and bits of Velcro is extremely different to what exists on Earth. So we have the same object playing quite unique roles in different contexts. And I think this is what makes it interesting, or this to me is what makes space technology interesting. I'm not very fussed with how a rocket engine actually works. I'm not saying that's not interesting, but you know, at the end of the day, these kinds of stories to me say more about how humans engage with space than do the SpaceX rockets or the enormous space stations or the incredibly sophisticated technology that goes to the moon. So on that note, I will finish. Thank you very much for your patience. I hope I haven't gone over time. And I believe we will have time for questions after the other speakers. So thank you very much for your attention.
Thank you very much, Alice. That was a very inspiring and thought-provoking presentation. And I think you made very clear that that divide between traditional technology and high technology is very much a construction. And that is an idea that we criticize very much in industrial archaeology, the idea of continuity and change that was proposed by Marilyn Palmer. I think that all of us, we will never look up there. We will never look at the stars in the same way. So you really gave us very new ideas. Thank you very much. I think Feng Shujin's problems are solved. Can you hear us? Can you hear us now, Shujin?
Yes, I could hear you. Yeah, are you okay?
Okay.
You could hear me.
Yeah. Everything is working good. Yeah,
Okay,
very well.
thank you.
So let's go with your presentation. Okay. So now we are coming back to planet Earth. More specifically, we are coming to Wenzhou in China. So we are going to learn about Wenzhou alum mine from the perspective of the archaeology of technology. This is a talk that is going to be delivered by Dr. Shujin Feng, who is currently a postdoctoral fellow at Tsinghua University and also at the National Academy of Innovation Strategy of the Chinese Academy of Science and Technology, where she is developing her research with the support of the China Postdoctoral Science Foundation. I think that Shujin is a good example of this interdisciplinarity that characterizes industrial archaeology, because she majored actually in engineering, but after that, she completed her master and doctoral studies here at USTB in the history of science and technology. And I would like to say that I had the pleasure of working with her and together with Professor Chan in the supervision of her PhD paper. With that PhD paper, Shujin was one of the first students in China to incorporate some theories and methods from industrial archaeology into her research. And to do so, she also went in 2018 to the Iron Bridge International Institute for Cultural Heritage, and now belonging to the University of Birmingham. Although that experience also gave her the opportunity to meet some colleagues from the Association for Industrial Archaeology. So now Shujin, she is engaged with industrial archaeology, the history of technology, and also value evaluation for industrial heritage. And she has worked with these topics on Wenzhou, which is the case she's going to introduce today, and also in Shougang, that perhaps you may remember because it was one of the places where the latest Winter Olympics were hosted. So thank you very much, Shujin. Good luck with your presentation, and the floor is yours.
Okay, thank you, Juan. Yeah. My computer give us a joke. Okay, now. Okay, now let me begin. Okay, good morning, good afternoon, and good evening, all friends from different countries. Yeah, thanks for your attention on my research. Many thanks, Juan, for your inviting. And many thanks the USTB and the UKAIA together with its young board members board. I'm very happy to have a chance to share the research with everyone. Today the presentation is based on my PhD paper and an article in the AIA review. It tries to focus on the archaeology of technology about Wenzhou alum. There are 5 aspects in my report. The first is the aims of the researcher, and the second is the literature review and archival investigation. The third is archaeological investigation of Wenzhou alum mine. The fourth is interpretation, and the last is conclusion. The aims, there are 3 reasons. Firstly, based on the field investigation and the archaeology of technology to preserve and restore the formation and dates contained in the mining industrial site. So, secondly, to review the industrial heritage of Wenzhou Alum Mine and to provide a comprehensive and detailed interpretation of its mining sites and alum refining sites. To create a new, thirdly, to create a new explanation of the characteristics and the connotation of the Wenzhou alum's technologies development. About the literature review and archaeology. Wenzhou alum is located in Fanshan, Zhejiang province. It's near the east coast of China. So this place has a mid-subtropical monsoon climate. So in the season of frequent typhoons and storms from May to September, so it's very destructive to Wenzhou alum mining site. About the history, Wenzhou alum has more than 600 years. Since the Ming Dynasty, it was 14th century. From this time to the earlier 20th century, production was mainly a secondary occupation to agriculture. From 1949, the alum industry moved toward nationalization, and it gradually changed from traditional to modern models of production. With the environmental protection, Wenzhou alum mine closed the operation of the water immersion method in December 2017. From now, Wenzhou alum is facing a transformation from production to industrial heritage protection. And in ancient, alum was used for dyeing and medicine. It was also used for producing sugar and paper. Besides, alum was also used for purifying water and stopping bleeding. In short, alum is a material of great industrial value. About the transportation routes, Wenzhou alum is near the sea. There are several wharfs and sports. They provide convenient conditions for the sea transportation of alum from Wenzhou alum mine to be sold in the world. There are 4 transportation routes for alum in this image. The red line is land transportation, and the blue line is water transportation. Alum was sold to Wenzhou, Shanghai, Ningbo, Fuzhou, and other cities, and even also was sold to the other countries. About the archaeological investigation of Wenzhou alum, the research tries to focus on the mining sites and the refining sites. The alunite in the mine is mainly from 5 mining areas in Changnan County. The geological department has confirmed that the reserves of alunite in Fanshan account to 240 million tons. It has been named World Alum City. Since 2017, we have investigated 7 mining sites and 10 refining sites. Today, I try to focus on 2 mining sites and 3 refining sites. They are mainly located in Dagang Mountain mining area and Jijiaolong Mountain 3V mountain. This table is the 7 mining sites. Most of them are abundant. Only Nanyang 312 edit is well protected. And this table is the 10 refining sites. Most of them are also abundant. Though Xiguang refining site is protected, it's not to be reused. And now Footwan refining site and the main plant area of Wonder Island was all protected intact and all reused to develop the industrial tourism. Xiguang mining and refining site was around 1900. There are dozens of mining caves, and number 10 cave was reused for refining alum sites since 1975. There are deserving pores, washing pores, critical pores, and other facilities. The left picture reviews the mining activities and the mining technology with the directional blasting of explorers saves of Xiguang site. And the right picture of Nanyang 312 edit, it was opened from 1956 until now. But now it is protected intact. The 6 major systems of the mine were very well preserved, and the electricity, lighting, narrow railway, and the air comprehensive, and all the facilities, all the equipment are also protected. Now, Nanyang 312 edit is used to develop the tourist attraction of alum mining industry. About the refining site, when Footwan Miners Village is built because of the mine, Footwan refining site is inlaid in the village. And it was from the late of 1950s until now. There are 5 furnaces, 2 stock yards, 1 sleeping and weathering pool, and 4 narrow escape course. All of them have been included in the 8th batch of National Trail unit. Main plant area of Wonder Island was from 1956 until now. It is protected with 1 slag of yard, 11 furnaces, 2 weathering pools, 3 deserving rooms. Each of them is including 2 roller sand washing pools and some filter workshops, several crystal pools, working shops, and also a shop. All of the time, the water immersion method was used for refining alum in Wonder Island mine. It was described in detail in 天工开物. And this production process only had 3 steps: calcining, dissolving, and crystallizing. But the process was improved with the workers' experience, so that by 1949, it had evolved to a 5-stage method. And calcining, steeping, dissolving, crystallizing, and coating. In the 1950s and the 1960s, the 5 steps production process was improved by adding several auxiliary steps to the as the images. And the interpretation about evolution of alum refining technology and facilities, including furnace, weathering, dissolution, crystallization, and other facilities. The first step is the first step in window alum to extract alum is to cleanse the alunite. The furnace is the most important facility to the alum refining process. It has experienced open air roasting and the stove type furnace, intermittent small furnace, and finally developed into a vertical continuous furnace. The biggest picture on the is simply diagram of the furnace modeled over 4 generations. The first generation shaped like a turtle shell was made of stone, a traditional alum refining stove. This furnace was very small and suitable for family workshops in ancient China. It could be found in the literature and the museums. About the second generation furnace, it was described in Tiangong Kaiwu. It was larger than the first generation. According to the inner shape of the furnace, the second generation furnace is divided into the urn-shaped furnace, the barrel-shaped furnace, and the bunker-shaped furnace. Because of the building works from the 1950s onwards, there is no surviving physical evidence of the second generation furnace. But the third generation was an intermittent furnace, as well as the first and the second generation furnace. By the end of the 1960s, the intermittent furnace was transformed into a continuous furnace. That is the fourth generation furnace. There is a large scale group of the first generation furnace in the window alum mine. It's one of the most visible structures in this landscape, industrial landscapes. And the evolution of the weathering facilities, it has experienced the leaching facilities of bottomless wooden barrel, the stone, bamboo, grass structure weathering workshops, and the brick tile wood structure weathering workshop. The picture on the right shows the Jijiao remaining site. There are one staking yard for alunite, and one weathering pool, one dissolving pool, and several crystallization pools. The picture on the low right foot is stone, bamboo, grass structure weathering workshops. It was made of brick and stone. The weathering of its facilities in main plant area of window alum or brick tile wood structures. There are different kinds of bricks and tiles in the weathering workshop, as the diagram in the in the upper and the right foot. About the process and equipment for washing and dissolving in alum making was following a step layout. It is based on the principle of least effort. As the picture shows, the burnt alunite ore in each pot was washed several times using the counter-current washing technique. At the end of the process, the waste ore in the first part was discarded. And the alum liquor in the first part was transferred to the crystallization room, and the dissolving process was ended. According to the theory of the location of industry, this process is following the principle of minimum transportation cost. This picture shows the dissolution and its facilities in the main plant area of Wenzhou alum. The roller washing pond shows that the fine alum grief was transported from the weathering room to the dissolving room using a belt. And the gravel was transferred by using a wooden hopper to the roller machine in the washing pond. These rollers are characterized by the use of wooden structures instead of metallic equipment. The second picture is the upright. Shows the layout of the dissolving room. The dissolving pond is separated from the washing pond by a way. The third picture shows the dissolving pond and the washing pond are linked by two holes. The conveyor hole was opened, and when the alum liquor was transported from the washing pond to the dissolving pond, when the alum and the alum liquor in the dissolving pond was reaching the right temperature and concentration, the discharge port was opened and the alum mother liquor was delivered to the next stage of the crystallization process. About the evolution of technology of crystallization, it has 3 stages. They are a simple crystallization pool, crystallization facilities in the mine sites, and semi-mechanized crystallization facilities. This picture shows the simple crystallization pool in Jijiao Ridge mining site. There are 19 pools, and they are bottomless wooden crystal bucket in the earlier. From 1970s, these crystallization pools are built with stone materials, but they are still in the pit and all sheltered from wind and rain with bamboo and wood shelter. The Xiguang alum refining site has a typical sense of recycling. Crystallization facilities are in mining caves, and there are 2 crystallization rooms with with 19 pores. The structure of the pore contains 4 layers, including a rammed earth layer, a felt, a gravel layer, and a slate. And its technology of crystallization works with slurry. The semi-magnetized crystallization facilities are used in the main plant area of Wenzhou alum. As the pictures, the rooms are structures of brick, tiles, and reinforced concrete. Alum mother liquor was transported by pump and rubber pipeline, and the crystallization pores are built with concrete slate structure. From this diagram of the structure of the pores, there are 4 layers of the pores walls. From the inside to the outside, they are slate, rammed wet lower, and oyster gray clay coating, and stone masonry with oyster ash and yellow mud. And there are 3 layers at the bottom of the crystallization pore. From top to the bottom, they are concrete pore bottom, rammed wet loess, and compaction of the original layer. Because of the time, I couldn't show more about the detail of the production process of the value of the alum. However, we could know the core production of the Wenzhou alum mine. And so, please let me do some conclusions. The first. Wenzhou alum shows the development of mining activities and the improvement of mining technology from the use of black powder blasting technology, and then to the directional blasting of explosives and mechanized mining. Second, the industrial layout and the production process of Wenzhou alum mine adopt or a stepped distribution. It reflects the guiding principles of the earlier mining and metallurgical industry. And that is following the principle of minimum transportation cost in alum production. Third, with the progress of science and technology, especially of the 1956, the site selection and layout of the alum workshop in the main plant area no longer followed the step-like distribution model. It was built in accordance with the theory of industrial geography, reflecting the complementary and connection among social economy, natural resources and environment, science and technology. The first, the alunite in Wenzhou alum allowed the adoption of traditional water immersion method of the production process technology or to produce potassium alum. This process has typical characteristics of localized or indigenous industrial technology in China. Fifth, Wenzhou alum industry site provides a unique historical witness for the traditional alum refining process technology that has disappeared, especially the unique example of roaster construction and drum sand washing equipment technology shows the important stage of human history in refining alum from alunite using traditional technology, and at the same time reflects the process of human understanding and utilization of chemistry. The last one, industrial archaeology provides detailed material evidence and data for the research of history of technology. In return, the history of technology also helps to explain the technical characteristics and connections of the industrial physical domains, and to review the industrial culture and the industrial society behind them. Okay, that's all. Many thanks to my supervisors for their care guidance. And thanks to the retired managers and workers from Wonder Alum. And thanks to all of the people for providing helps in my research. Okay, that's okay. Thanks everyone for your patience. Okay.
Okay. Thanks to you, Eugene, for your presentation. Good job. I am proud of having been your PhD co-supervisor. So well done. So we continue. Finally, we are going to learn about not about the history of technology, but about how we can preserve the materiality of that history of technology. And for that, we count on Jeffrey Wallis, who is going to deliver the paper Developments in Practical Engineering Conservation, the works of Dorothea Restoration Limited. Jeffrey, he's a mechanical engineer from the Bath University and the co-founded of Dorothea Restoration Engineers Limited, a company that he directed for over 30 years and a company for which he is now an external consultant. So in all these years working with the restoration and conservation of machinery and engineering works, he obviously has acquired a good deal of practical experience and expertise in the restoration and conservation of historic metal works, machinery, and also traditional mills, and knowledge and expertise that he has also transferred and he is still transferring to new generations with the delivering of courses in several universities, both in the UK and beyond. Jeffrey is a very active and engaged person. He is a trustee of the Museum of Bath at Work, a museum, by the way, that is going to be one of the key visits of this year, 50th anniversary of the Association for Industrial Archaeology conference. So it will be very good if many of you can also attend this conference in Bath from late August to early September this year. And he's also a founder and director of the National Heritage Iron Work Group, a past president of the Newcomen Society, and a council member of the Association for Industrial Archaeology, for which he created the Joint Members Board that is also organizing this workshop. So thank you very much, Jeff, and please, the floor is yours.
Thank you very much, Juan. Can everybody hear me all right?
Yes.
Okay, very good. So good morning or afternoon or evening, everybody, and thank you for your invitation to make a presentation. I'm going to be talking a little bit about the company that I jointly founded with others. We're having our 50th anniversary year next year, so that starts to make me feel a little bit old. We've done probably, well, several hundred, many hundred projects over the years. So talking about the developments that I've seen in just 30 minutes is frankly impossible. So apologies for what I leave out. The company is currently turning over about 1.6 million. That's 1.8 million euro. There are 17 full-time staff. The company doesn't sublet work, including 2 directors, my son John, who took over the company about 15 years ago, and his colleague, Ruan Vesta. So I think we're probably still the largest restoration specialists in the UK, specializing in the restoration of historic machinery, steam and oil engines, museum exhibits of almost every time, except February, I should say, Alice. Looking forward to that, getting involved in that. Get involved in a lot of electric drives on machines as because of the problems of getting the traditional materials like coal and the pollution that they make. The company are traditional millwrights, wind and water mills all over the country. And much of the company's work now is the restoration of structural and architectural metalwork, particularly cast and wrought ironwork, whether that be bridges or glass houses or conservatories or gates and railings and so forth. And for the last 40 years, we've been doing a lot of consultancy, so condition surveys, specifications, operator training and so forth. Now, one of the earliest developments was in 1988. When the company was first set up, we had a lot of people approaching us, and clients would come to us and say, will you please come and fix my my bridge or my conservatory or whatever? And we'd say, well, look, we're contractors. What would you like us to do? You tell us. And they'd say, no, you're the specialists. You know your field. You need to tell us what you're going to do, which is a rather strange situation for a contractor. So unusually for a contractor, we spent a lot of time as directors discussing what we should be doing. And we came up with these conservation ethics, and they haven't changed in the period since then. So basically, we're looking to do as little as we can, minimal disturbance, minimal loss of evidence, retaining as much of the existing materials as possible, repairing and consolidating rather than renewing, using reversible processes wherever possible. And I'm still trying to work out how to drill a reversible hole to put on a repair plate. We will add material to reinforce, strengthen, prop, tie and support and so forth. It might not look very good, but it's good conservation practice because it's minimal intrusion. We would like to use traditional materials and techniques wherever we can. And if we do have to use new materials, and almost always we do, we'd like to make them distinguishable from the originals if we can, so that we're not confusing future generations. And ideally, we would like to be recording before, during and after our work. So the conservation philosophy, of course, hasn't changed, and indeed is common to, I hope, all other fields of conservation, whether it be paintings or books or whatever. But of course, the materials, equipment and techniques have developed, and that's the basis of this very brief lecture. So our challenge really is to uphold our philosophy, our ethical base, if you like, whilst also delivering what the client wants. They are, after all, paying for what we do. We have to give best value for money, or at least work within a budget. We have to try and deliver on time, and sometimes that's very, very important for a client. We need to be producing the maximum longevity. In other words, the first time to major maintenance, we must make things maintainable. And of course, delivering a safe structure or machine these days is critical. And it's very difficult because usually these artifacts, these structures and so forth were designed for functionality and not for safety or maintainability. So we have to try and wrestle all those things into a credible situation whilst as part of our restoration work. We'll just look a little bit at some of the materials now. real wrought iron, as we call it, or puddled iron, is the predecessor of wrought iron, of steel. And steel took over really when the processes for producing it were perfected in the late 1800s. But before that, the blacksmith would have to use this traditional material of wrought iron. And this is how it was made. I'm hoping you can see my cursor. Top left photograph, pig iron, cast iron that has been smelted, is thrown into a reverberatory furnace, and it's then heated for several hours and reduced. The carbon in it is removed, and eventually the spongy mass, middle photograph top, is pulled out. It's white hot, and it's shingled or hammered to refine it and compact it, top right, down to the bottom left. It's then rolled and comes much thinner, but it's not very good quality at this stage. So it's reheated, bottom right, put into a furnace again, made white hot, re-hammered, re-rolled, and it may go through that process several times to refine it. And it comes out as a very pure form of iron, very ductile, malleable, and the blacksmith, of course, could make anything with it. It is no longer made anywhere in the world now, except experimentally, but this type of material is still available from the real wrought iron company, whose details you can see on the bottom there. Continuing with traditional materials, we try and use them wherever we can, wherever they will be practical. So on this very tall windmill, for example, here in Lincolnshire in the UK, the brake wheel, which stops all this machinery up here turning, is made of the traditional material. It's elm, chosen for its interlocking grain so that it doesn't split. And we love to use plain bearings. This is the bearing that holds that great big rotating assembly up. There are very efficient modern bearings nowadays, and we don't use them anywhere where there's damp conditions. Windmills and watermills are pretty much guaranteed to be damp, and if you put modern bearings in, they rust, they seize up, and give a great deal of trouble, whereas the traditional bearings will put up with a certain amount of water. And you can see this traditional bearing here on the wooden frame of that windmill. And the shaft that runs in it must be strong. Traditionally, it would have been made of grey cast iron, and they tended to break here because this overhung load, which is where the sails or the stocks are fitted, tends to break the brittle shaft off at this point here, the neck. So this one's been made of a modern grade of iron. It was made in the traditional way, but with a modern grade called spheroidal graphite, and that is very, very strong. So it's worth making that modest change. It's not visible, but it is structurally very important to get a safe result. Similarly, I don't know if you noticed on the top of that very tall windmill, right on the top of the cap was a tall finial. It's 13 meters from the ground, and it's never going to get maintained. So it's made of a durable hardwood, and you can see we're coating it with glass fiber, because frankly, anybody trying to get up there to even paint it in the future is going to be in great danger. And putting a scaffolding up 30 meters is extremely expensive if all you're doing is painting the finial. Continuing with safety, our staff safety is clearly very important to us. And as you would expect, we produce method statements and risk assessments. We brief our staff very carefully before they work. But the secret, frankly, the practical way of delivering safety is for experienced operatives who've seen it all before, leading less experienced. So this is a sort of continuous informal process where the older people are mentoring and tutoring the younger people by simply working with them and showing by example. And that works far better than any sort of formal training or whatever. Of course, both parties, the older and the younger people, do have to be willing to buy into this process. The older people must be willing to pass on their skills, and the younger people must be willing to accept them. Health and safety for our clients is very important too. we have, for example, restored this dangerous piece of machinery. We're now going to hand it over to a museum. So we have to think about, for example, guarding and handrails and so forth, and how we hand over. And there are occasions where we have actually refused to hand over a structure or, sorry, a machine usually, because we don't think that the client has the necessary personnel or training or management capability or whatever to run the thing safely. So we say, look, we've done the work, we'll prove to you that it works, we'll demonstrate it, but then thou shalt not use it because we don't think you can do it safely. That is our duty of care, I'm afraid. But we try and do better than that. We'll produce an operating and maintenance manual. We'll train the operators, do whatever we can to make it safe. And of course, then the machine being old tends to wear and have all sorts of problems. So we provide ongoing maintenance support. And if you're dealing with machines that have water or steam associated, we do have to think about environmental control as well. So we try and help there. Fitness for purpose is a legal concept which is very important to everybody. This is a water-powered flour mill still working in the Midlands of Britain, and it is in a working condition. So who is responsible for making sure that the visitors are safe? This is really a problem. Who has, well, what is its purpose for a start? If it's going to be fit for purpose, what is that purpose? Well, it was a flour mill, and it still mills flour. So is that its purpose? Well, not really. It earns its keep. It justifies its existence by entertaining the public of all ages. So they come in and find a dangerous piece of machinery. Whose responsibility is it to keep them safe? This was actually managed in this particular situation by the simple expedient of a piece of rope going across, and the operator or demonstrator standing on one side and ensuring that the public stand on the other side, and he can see what they're doing, and he won't run the machinery unless they are paying attention and have been briefed and he feels it's safe. And he will only allow people in for guided tours. So that's more about movement than hardware to keep people from putting their fingers, for example, in this rotating cog up here. Lorry-mounted cranes are wonderful. They've revolutionized the way in which we work. Wonderful development. You can see this lorry-mounted crane is able to reach off the end of its lorry and onto a trailer behind. Absolutely wonderful pieces of machinery. And road mobile cranes are even better. They've enabled us to work on large assemblies at ground level and then hoist them up. Traditionally, something like this would be made in a large number of pieces, assembled on the ground, marked up, and then taken apart and transferred, for example, in this case, to the top of the windmill tower. Nowadays, we do it all at ground level, and we can safely and economically then just pick it up, whatever size, whatever weight, no problem, and put it wherever we want. Modern cranes are truly wonderful and have revolutionized our business. And there's my son just lowering, or rather directing the lowering of this very heavy cap onto the top of the windmill and onto a very carefully laid out leveled circular curb, because this entire cap has to turn so that the sails can face the wind. It's quite exciting looking down from these this sort of height. It's a great pleasure to be working on this sort of thing. I have to admit, it's fun. That's why I joined this company, and have thoroughly enjoyed this field of work ever since. And that's what we're aiming at. There's many tons up there. The whole lot turns under the power delivered by this fan. So the sails, which haven't been erected yet, would be on the other side of this. And if the wind is on the side of the sails, it's on the face of that fan. So the fan turns and it drives the whole of this structure round until the sails here would be facing the wind. Truly wonderful. Royal Exchange in London has a 2-meter long copper grasshopper as a weather vane on the top of the dome. It's the Gresham family emblem. And I had a phone call one Monday morning from a very worried manager who said, one of the legs of our grasshopper has fallen off and gone through a glazed dome. Get up here very quickly and put it right, please. So this is the offending item. Because of modern cranes, we were just able to phone up and literally go up there and get it with the crane. And here it is in its workshop, having lost 2 legs, in fact. But the problem here is the traditional material. Copper is very corrosion resistant, and that's why it's used for weather vanes. But the problem with a shape like this is that the wind vibrates the copper and it work hardens, and that's why it cracks. So you have to soften the copper, put it all back together, and then reinforce inside with some modern materials. If I remember rightly, it was stainless steel in this case. So this is a combination now of modern and historic materials that is then finished with the traditional 23.5 carat gold leaf, taken to site, and the wonderful cranes available nowadays are incredibly sensitive. They move, they can just move a few millimeters if necessary. They're strong enough to carry everything you need. So that in that basket, as it's called, are 2 operators, all their equipment, and hanging on the bottom is a 2-meter long copper weather vane. And the whole lot then can simply be craned in one operation. It's again quite exciting up there when you start looking down and seeing this bending like a fishing rod, but they work very well. And the view is very good too. Drone surveying, of course, is very much part of life nowadays. This is a luxury hotel being redeveloped at Droitwich near Birmingham. And it has iron finials. And of course, there's no way of surveying them from the ground unless you put up a very, very expensive scaffolding, only to find that there's nothing wrong with the metalwork. So we've invested in a simple drone. They're actually very effective. They have very good video and stills camera capability. This one, you can probably just see the controller is actually clipped on to here, and it is the telephone that simply records the videos and the photo digitally. The legislation is quite tight around these machines. You have to have a commercial license. It takes about 40 hours of training, because you have to learn all about the certificate of the rules. You mustn't fly these things, for example, in proximity of airports or anywhere near flight paths or helicopter flight paths. There's quite a lot here, and you have to have the owner's permission, and you mustn't fly within a certain distance of buildings where you haven't got permission. So there's a lot to this, but they're very, very useful tools, and can do 2 things. They can identify problems, and you can see there's a problem here, but they can also identify that there's no problem. So you can do a quinquennial, a 5-year survey, for example, within a day, very thoroughly. You can get video or still evidence that there's nothing wrong, which has saved, many thousands of pounds of scaffolding cost. So they do have their use, but usually you find that actually, if there is anything wrong, you can't do anything about it remotely. You have to just put up the scaffolding and do it traditionally. Let's move on to 3D scanning and printing. We have our own scanner. This is a handheld scanner. We've got our own 3D printer, and it's used for proof of concept trials for all sorts of components. They can be made very cheaply, and that's quite a useful tool. also for reproducing historic shapes. Now, this is quite difficult to reproduce. In this particular situation, the client learnt how we were going to be doing this. They said, what I would really like is an elliptical version of those because it'd be easier to hold. And of course, that's very easy to do digitally. You can elongate something. And so I'm afraid we couldn't get out of elongating it and then making a pattern. I'm sorry. We done on this one was sent the CAD file to a 5-axis CNC machine, bottom left, and that was used to mill out the elliptical bronze replicas of these things. So this is a situation where modern equipment has enabled the client to ask us to do something which frankly isn't conservation and is not really in accordance with our conservation principles. And that's one of the problems, that the modern developments that are wonderful in doing almost everything, they will usually reduce the price, the cost. They will often increase the actual facilities that you can offer, and maybe the accuracy and so on. But it really is a problem if you're actually basing your business on conservation ethics. So we may have to discuss that after this presentation. These machines are wonderful, though. They can do all sorts of complex shapes and undercuts and hollow shapes and so on. This is 3D printing of a pattern. This rather wonderful cast iron thing statue was on the staircase at Bristol University until students stole the urn on the top. So we were able to make a replica and change the size of it until it looked to the client as if it was correct. And then we simply reproduced it in iron. Another 3D printing situation here, a chain wheel and chain driving a watermill for the National Trust. Both the chain wheel and the chain were extremely worn, so they're becoming dangerous. So we had to make a new chain that would fit a worn chain wheel. And that was done by making a welding jig by 3D printing and then covering that with a ceramic so that we could actually weld in that jig so that all the links came out exactly the right size and all the same. So a very useful process. Slightly bigger in scale here, 1 meter high bronze lions from the embankment there. They used to have mooring rings, but the ships have sort of damaged them and pulled the rings out. And so we had to replicate a number of these and repair quite a large number. So that was done by handheld laser scanning. So this is the 3D image. There we are. That's the cloud point map of a 1 meter high bronze lion. So that was used then for laser, for 3D printing of patterns. Top left. Right, from that a bronze casting was made. That was then fettled and trimmed up. Bottom right, bottom center, this is the new casting that has been fettled and blasted. And this is the final casting. Notice the beautiful finish on this. This is called patination. You notice the mane is a slightly different color to the face. This is a chemical treatment that simply converts the surface to a sort of stable patina, as it's called. And you can use different chemicals to get different colors, which is absolutely wonderful. Another advantage of this process is that you've got the CAD version of this. And if you shrink it right down, you can produce small gifts. There we are. This was one that was given to me as a birthday present. That's one of the perks of being the father of the director of the company. Harcourt, Kibworth Harcourt Mill in Leicestershire is a post mill. It has a timber post, it's a tree really. And when we came to restore this, we found that this has actually gone rotten. As you can see on the right here, there's a big post there and it cannot be repaired because of all the machinery around it. So it had to be monitored very carefully. And so on that post, if you look to the right, a number of sensitive tilt meters were fixed and they were monitored from nearby, from a house nearby. And they were so sensitive that when we were actually hanging the sails on, you could see the whole mill deflecting. And this, of course, this machinery enables the mill to be monitored when the wind is blowing in the future, to see whether that damaged main post is coming to any harm. And nobody minds it flexing, but what it mustn't do is take on a set and then gradually move to the side. And that's what this equipment can identify. The whole place was scanned in great detail. We don't do drawings anymore now. These scans are so accurate that we can produce both the as-found drawings and the as-built drawings digitally in about a day, whereas it would have taken a month previously. And these scans are so accurate that we were able to use the scan data, which is about 2 millimeter accuracy, to see how the main timbers had distorted before, during, and after the work that we were doing. This whole body of the mill, 16 tons of it, had to be jacked up. And of course, that enables the timbers to flex. And we need to know what those timbers are doing. And of course, having got all that cloud data, it's relatively easy to put it together to enable the structure to be viewed inside and out, in its context, in 3 dimensions, and indeed to fly through it. And I'll put this, if you like, on the chat, but this is the YouTube video that you can see for free, flying through this mill. Absolutely fantastic. And I think that there's a huge potential for this this digital imagery, particularly for virtual reality. Now, we have virtual reality now, and it's becoming cheaper, and it will get cheaper and easier to use in the future. And I think for our business, we have a fantastic opportunity here for example, for remote site surveys. We work all over the country, and to do a survey of one day in north of Scotland is actually rather expensive for the client. But if the client could use the 3D and 360-degree sensing equipment that is now available, we could stay in Bristol using this sort of headset that you see on the right and do a survey. Equally, we could be advising our site, our site staff, if they're working on a site somewhere, we don't have to go and see what they're doing. They can ask us questions and we can answer them in real time if we can both use this sort of equipment. And that's really important to us, because if you remember, the safety of the staff and the quality of the job is coming from the communication between the more mature, the more experienced people and the younger people who are our future. And of course, there's a lot of potential for publicity for the business. Equally, there's huge potential, I think, for the owners of the heritage on which we're working. Publicity again, visitor engagement. This is a fantastic way of not only interesting visitors, but teaching them as well. You can augment the virtual images and give all sorts of messages that can be tailored to any age group and in any language. And there's a huge potential here. Operator training, I explained how important that was, and we can do that remotely, potentially, which would be of great benefit to the owners of historic machinery and dangerous things like wind and water mills. And what about remote visits? This is an international conference that's taking place. It would be very interesting if we could be using this equipment much more than we do now for international visits to some of our wonderful sites. Indeed, I just wonder whether perhaps the East-West Conference attendees will be able to visit each other's sites virtually in a few years' time. I hope that's the case. Thank you for your attention, ladies and gentlemen. Over to you, Juan.
Thank you. Thank you very much, Jeff. And I really hope we can actually show each other sites and everything virtually. That will enrich very much the experience. Thank you very much for that very informative, actually a masterclass, I would say. And I am fascinated with the possibilities of all these new technologies in the field of conservation and restoration, and also in the presentation of these artifacts and sites. I can imagine how much your work has changed since you started to work in this field 30 years ago or so till today. And it is really admirable how you have kept up to date with all the new techniques, technologies, and resources available. So it's time now to start the discussion section. Everyone is welcome to open cameras and microphones if you want to, or you can also text your questions on the chat facility if you prefer to do so. So far, we have a question for Feng Xujin by Mario Bruno Pastor. He would like to know if there is any typological correspondence of the different pharmacies generations to other activities or sectors still in use, namely the first generation, that turtle, and the second generation pharmacies.
Oh, okay, thank you, Pastor. Yeah, it's a very good question. Yes, the first and the second generation faunas, they all didn't, they all, because many years ago, they haven't left the physical evidence, but we could find them in the museums and the literatures. Maybe in 1990s or 1980s, they're only small, the second generation faunas. Yeah, but I know it from the altered engineers and the retired workers, but there is no evidence in our investigation. Yeah. And besides though the faunas, the first and the second or the first faunas uses the traditional method, but the alum is very clear and is very beautiful. Yeah, there have alum. Yeah, it's very beautiful and it's very clean.
Mm-hmm.
So thank you, you question. Yeah.
Thanks.
Thanks, Eugene. Any other questions? I have a pair of questions myself, one for Alice and one for Jeff. For Alice, well, there is something I normally discuss with my students of archaeology, of industrial archaeology, that, well, I normally tell them that in archaeology, the meaning of the artifacts does not come from the artifacts themselves, but from the physical relationship between the artifact and the spatial context in which the artifact is found. But I guess this does not work with the space junk that is in orbit, because, well, there is at least not a static, not a fixed context for those artifacts. So how we can figure out more, how to know more about this junk that is in orbit?
Yes, that's a great perspective one, because this stuff is moving at high speed, moving continually. So its relationship to each other changes a lot in a very dynamic way. But there's also kind of stabilities within that sort of vast morass, that vast density of things. So we have particular orbits that are more stable than others. We have areas of higher density, areas created. So like geostationary orbit is a designed orbit, if you like. Things are put into it for a particular reason and they stay concentrated there. So they have a relationship to each other. And you also have, the sort of intersections between polar and Molniya and equatorial and other kind of low Earth orbits. So it's like a statistical stability, I guess. so that one-to-one artifact relationship might not be as simple as if we excavate it from the floor of a trench. But if we're looking at it statistically over time, then I think you start to see relationships and trends. What we're seeing right at the moment is with the launch of the Starlink mega constellation since 2019, we now have a preponderance of a certain kind of satellite in low Earth orbit that is going to show up in that way. And even though individual components of it may drop in and out, the structure has a certain kind of stability to it. So it's a very different kind of archaeological record, I think. The other aspect to it is that there's no separation between the stuff, what we might say in Michael Schiffer terms, the systemic and the archaeological contexts. So the stuff that's being used is up there jostling around with the stuff that is junk. So they don't separate themselves out by gravity as they do on Earth. So I agree. I think this is something I think about a lot and have come up with different ways to describe, none of which I think are, perfect, but it challenges what we think those relationships are and what we think those objects are defined by their relationships, because what holds on Earth does not hold up there. So probably a very fuzzy response to your question, but I think that is excuse me, that is a key part of how we have to think differently to look at space.
Yeah. Actually, from my point of view, that is one of the great values of space age archaeology, that it forces us to rethink archaeological theory and methods, because it's also this idea of yours that I learned reading your book, that in space archaeology, in places like the International Space Station or Mir, well, these places challenge us to think the divide between site and artifacts, because they are at the same time sites containing people and artifacts, but also they are artifacts made by human beings. Sorry. So yeah, I find this work of yours very interesting, and also I think it's really changing how we think and do archaeology.
Thank you, Juan. And could I add here, for me, it was so interesting to hear Feng and Jeff talk, because we're looking at older materials and technologies, some of which are clearly, equally efficient, or in some instances more efficient than contemporary technologies. And when thinking about how we might adapt human materials and processes to space, I do wonder if sometimes those older materials and technologies might not, in fact, be more ideal than the things that are being developed contemporarily. And some of the, like the industrial processes at the Alum mine, like if people are going to go and mine the moon, which I'm sad to say they are, it's almost too late to stop them, but we could still try. Maybe there are actually efficiencies or processes that we can see, like in the Alum mine, that would work better than the fancy new stuff. So that's something that's really given me something to think about listening to the presentations tonight.
Very good. Thank you very much. And Jeff, I liked your presentation very much, especially the part about the ethics, because that is also an idea that I discuss with my students very often. There is something that some other scholars have criticized, that practice of restoration as new that you have been mentioning when you were talking about this ethics on restoration. So for me, it's interesting to think that obviously as archaeologists, we are interested in the footprints of use. And we think that keeping all these footprints of use and even wear, it is very important to use the artifact as a document, and they have actually a very important value as a source of information. But so my question is to what point, or how to find a balance between keeping all these footprints and keeping all this wear, and keeping the machines on the other side, maybe well in a good condition, or even operational, because well, I do think that the essence of a machine is to work. But if the machine becomes an archaeological object, let's say, well, it cannot work anymore. So what should be more important to preserve all these footprints of use and even damage, or to keep the machines working, or how to find a balance between these two different dimensions?
That you've hit on the absolute core problem. The ethics that I set out there, the sort of philosophical principles, are very easy to write down. Actually, they're not that easy. It took us a long time and a lot of discussion to work out what the sort of fundamentals were. But when you write that down, you say, well, we've got to, for example, try and preserve the evidence. And then you say, well, what is the evidence? What evidence are we trying to preserve? Is it the artifact itself or its context, or the article in its context? And of course, much of the portable heritage that we have is well out of its context. It's in a museum or it's up in space or whatever. And so we haven't got the context. So we're thrown back again now to the evidence contained within the artifact or the structure or the machine. But as you say, if it's a working piece of machinery, it is definitely going to change. It will decay, or it will rust, or it will break, or it will wear, or whatever. So we've now got to try and understand and preferably record that process. Otherwise, after a few days or weeks or months, and certainly a generation or two when memories have faded, we have lost the evidence. So there is a course of thinking that is the museological course, if you like, is that we'll put these machines into preservation, into a museum, or just lock the door if they're in situ, and try and not spoil them or spoil the evidence. Well, that doesn't work because nature takes over and you get rot and rust and vandalism and arson and so forth. So you've got this sort of circular argument. And that's why we had to sort of break into that and say, well, what are the fundamentals we're trying to do? And I think we have written them down. But what we've learned is that whilst we can agree on the fundamental principles, we hardly ever agree on how to actually practically implement it. And that's because there are so many people making inputs to it. There's our management, our directors, our staff, there's the client, there's probably an architect, there may well be a structural engineer, there may well be Historic England's conservation people, there's the poor old client who's trying to make sense of all this and pay a bill, and it's really very difficult to do. So I think I'm probably just explaining the problems again rather than answering your question, Johan. And I think that means there probably isn't a clear answer. Have I managed to get through that one?
Yeah, I agree. There is no answer for this question. At least I don't have any either.
No, and when I run conservation courses, I always bring up this subject and show one or two simple examples. And it's very quick. We very soon realize that there is no clear best answer. So I end that conversation by saying, well, look, if we can't agree on what we're going to do, what is the point of having fundamental principles? And the answer to that question, of course, is if you don't have those fundamental principles, you have no idea from the point from which you're starting your discussions or what you're actually aiming at. The fact you can never actually get there is not the problem. The problem is if you don't actually agree or know what the fundamental principles are.
Mm-hmm. Yeah, very good answer. Thank you. Good. Any other questions? Anybody? You can use the chat if you prefer so. Okay, so I think that was for today. Thank you very much again, Alice, Sujin, and Jeff for your fantastic presentations. thank you very much for all the people who joined today. I hope you found these talks as amazing as I did. And thanks also to Bill for taking care of all the registration and the technical part that, well, without that, we could not have this workshop. So we will be back again on November, that time to discuss the architecture of industry. I hope to see many of you again on November, and enjoy your Saturday and the rest of the weekend. So thank you very much again. Muito obrigado, and see you in November.
Thank you very much.
Thank
Enjoyed
you.
the
Thank you.
fantastic.
Cheers.
Good night. Good night, everyone.
Bye-bye.
Bye.
Bye-bye.